So, if you want to go into study you haven't seen yet, if you open up, the MyMath Lab, in every section of your homework, in the study command, it has a breakout for all the different parts.
But that's what I want, cause I know the professor, listen. I feel like me and you already know about how we should study together. I know you had study, if I went back to your school, I bet you say he was very good at study, he helped everybody.
Oh, yeah?
Is that true?
Can either confirm or deny it.
So you don't necessarily have to study together, you can study on your own and it's perfectly fine.
So you study all through college, you study by yourself?
Yeah, you kinda have to, yeah.
All by yourself? All those hard classes?
Yep.
You never thought about, let's try
I
to,
took
this.
6-week course of.
Was your professor
Some people just study better alone, sometimes it's more efficient to study alone versus you're in a group and you have
I'm doing the second
people
part.
just all in different directions. It's not as efficient sometimes.
Or you just felt like you was at Harvard, you couldn't, y'all couldn't execute?
I hope it doesn't happen.
Sometimes it's just more efficient to study on your own, it's better use of time.
Yeah.
How did y'all professors prepare y'all? Did y'all write on,
I
you
need
know,
to be
chalkboard?
like competitive and get into nursery.
Yeah, they were chalkboards.
I knew you guys were on chalkboard, I'm like, I
But
don't use.
do good, that's.
Okay, let's get started, guys.
Who ya?
Yeah. So as you guys probably know, there's a test coming up. Test will be available at the end of class today and won't be due until the beginning of next class, so on Monday. So you can study all weekend if you want, or you can get it away with and sleep easy if you want to get it over with tonight. Yeah.
Will the test let you know like which questions you got wrong?
Eventually it will. It'll just, when you take it this time around, it'll just let you know your score, and after everybody's taken it, it'll be open for review.
Yeah.
Yeah. So today what we'll do is, basically we've gone over all the concepts already. Today we're just gonna practice more on that last concept we talked about, which is probability. We're gonna solve some problems together, and have a little study group. And get you in the mindset of solving problems.
I knew me and you had that connect, I knew.
Oh, yeah.
I knew it, man. Like, I know I seen him before.
Are you graduating soon or no?
Alright, guys.
When?
So first off, do you guys have any questions on the homework?
I did have one question, you go ahead.
I got quite a few.
Oh, okay. I have one homework question, we can go over it after class if that'd be better, but it was the ATM pin homework question.
Okay, that's actually relevant to what we talked
Okay,
about.
I know we did a very similar thing in class, I used the multiplication counting,
The little toxic.
principle for it, and it didn't work, so I just wanted to go over it.
Okay. So go ahead and give me the details of the
So it
problem.
was a 4-digit pin on a 5-digit keypad, and, repeating numbers were okay for it.
Okay,
So I multiplied 10 times 10 times 10 times 10, because of the 10 data points 0 through 9.
okay, so the key thing is that it's a
Yes.
5-digit keypad.
That's what I was wondering,
Yeah.
if
So
that's-
now you only have 5 options for each digit and not. the
So
full
not
digit.
9, or not 10?
Not 10, right.
Okay, that makes sense, okay, thank you.
Sure. Okay,
I
good.
got a few, I wanted to pull them up here because let's just say I got a little frustrated, so I took pictures of them to make sure I can get it right, so didn't forget. So, the first one was, a corporation must appoint the president, a CEO, COO, and CFO, and then a committee with 5 different members. There's 16 qualified candidates for the 4 positions and the committee with 5 members. Officers can also serve on the committee. And then it says complete the parts.
So how many members on the committee?
5, we're sorry. With the officers being able to serve on the committee.
Okay. Alright, good. This is a relevant question to what we did with counting, so let's go over this. So let's first do the first part. Part A.
So that one is 16 eligible, anybody can get selected for that, but they have to choose those 4. Anybody could qualify for that, so that's gonna be your permutation. So that should be 16P4.
Okay, excellent. So let's build up to that, that's correct. So let's build up to that. So,
My God.
so any group will have these 4 office positions in it. So we're gonna list out the 4 categories that must belong in every possibility of these 4 office positions. And then for the first one, which represents the president, you ask yourself how many options are possible to choose the president. And you have the full 16. So there's 16 options for president. There's, how many options for COO?
15.
Yeah, so you can't have the same person be a different officer, that's stated in the problem. So because of that, there's only 15 options for the second office. And then the third office position, you have 14 and then 13. And then by the rule of counting, you just multiply everything together. And by definition, because you're starting with 16 and you're multiplying downward at a time until you have a total of 4 things, this is 16 per each 4. And keep in mind that this also implies that order doesn't matter among the particular 4 people that's chosen. Order does matter among the 4 people that are chosen. So for example, if you pick a particular set of 4 people, and then you change the ordering of those 4 people, should that count as another possibility?
Yes.
Yeah, because imagine you have an arbitrary set of 4 people, like person number 7 is president, person number 3 is COO, person number 12 is CEO, and person number 2 is CFO. Imagine you have those same 4 people, but just in a different order. Well, the meeting before that is person number 1 was president, or person number 7 was president, and the meeting now is person number 2 is president, so these have different meanings, so they should count as different possibilities. And so because order does matter among each particular group of 4 people you choose, then we say order matters, and we stop here and just multiply the 4 numbers, and that's 16 people. So now let's go on to the second question. If you have a 5-member committee, now each committee that's counted as a possibility has 5 members in it. And then again, you ask yourself how many options for the first member, and this is where that stipulation of the problem, where it says that the same person who is an officer can still serve on the committee, so that tells you that you have the full range of the 16 possibilities, for 16 options for the first person on the committee. And then the second person on the committee, now that you've picked 1 for the first member, now there's 15 options for the second member, and so forth. But now what's different about this problem is that for every 5-member group, does the order of the 5 members matter? If you switch the order of the same 5 people, does it count as a different committee, or is it the same committee? It's the same committee. So we say that the order doesn't matter, the order doesn't, different orderings of the same 5 people don't get counted again, so therefore order doesn't matter. And we would divide by the number of ways to order the same 5 people, so 5 factorial. And by definition, this top part is 16 per meet 5, and then the bottom part is 5 factorial. So by definition, this permutation divided by this factorial is a combination. So this is 16 combination, or choose 5. All right, any questions?
This is C16
Yeah, 16C5. Versus the previous one was 16P4. And if you ever wonder whether order should matter or not in this problem, do the same thing that we did over here. Specify a certain arbitrary possibility, like these 4 people, and then maybe add another person for the 5 people on the committee, and then use those exact same 5 people or numbers, and then switch the order and ask yourself, should these be counted as 2 different possibilities, or are they the same possibility? So in the previous case, these should have been different possibilities, but in this case, the same people in a different order is still the same committee. Okay, any questions? Sure, we can address some of those.
So
I think it'll be helpful for everybody.
Just say, I'll just go over one more then, because it just confused me, so,
Yeah.
Alright, so it says testing for disease can be made more efficient by combining samples. If the sample from 6 people are combined and the mixture tests negative, then all 6 samples are negative. On the other hand, one positive sample will always test positive, no matter how many negative samples it is mixed with. Assuming the probability of a single sample testing positive is 0.1, find the possibility of a positive result for 6 samples combined into one mixture. And then it asks, is the probability low enough so that further testing of the individual samples is really necessary? But it's mostly just it's the probability of a positive test result is some number.
Okay, good.
So,
So this is a good question to do. This relates to the concept that we talked about last time, the probability. And last time we just talked about the concept, we didn't get a chance to really practice. And actually, this is a good practice problem. So this tells you that the probability of one sample testing positive is 0.1. One single sample is 0.1. And so what you could do in real life is you could just test one sample at a time to see whether they have the disease or not. But it turns out that if 90% of the time people test negative, it's kind of wasteful to do that because 90% of the time you're going to get a negative result anyway. So what people do is they're going to combine results. So in this case, they're going to combine 6 samples into one. So a sample of 6. And then for those 6, you're going to test the whole batch. And most of the time, all 6 are going to end up being negative, so you know that every single one of those has to be negative. But once in a while, the batch of 6 will end up being positive. So then that tells you that one of those, or at least one of those, has to be positive, and then you go and test them individually. And that ends up saving more money and being more efficient. So the question is, in this problem is, what's the probability that a sample of 6 will be positive? So if the sample of 6 is positive, what must be true for the individual samples within the
At
6?
least one of those individual samples has to be positive.
Very good. So one or more of those individual samples of 6 has to be positive if the sample of 6 turns out to be positive. So the probability of the sample of 6 is positive means that at least one is positive. And oftentimes with these probability questions, the hardest part is just converting the original statement that you're trying to find the probability for into logically equivalent statements. So the hard part often is the logic and not necessarily the statistics. So at least one is positive means that either 0 samples are positive, or one of the samples out of 6 is positive, or 2, or 3, or 4, or 5, or all 6 is positive. So at least one is positive means that either 0 is positive, or 1 of the samples is positive, or 2 of the sample are positive, and so forth. 0 is not included. So either 1 is positive, or 2, or 3, or 4, all the way up to all 6 is positive. So last time we talked about a handful of mathematical rules to find probabilities. So the rules we talked about are we talked about the classical definition of probability. Classical definition is the probability of a desired event.
Means to find the total number of possibilities from some sequence of events, right?
Okay, so this is the number of desired events divided by the number of total events. So we did an example, simple example with the probability of heads for a coin. We said that you could look at a single coin, how many total events it has 2, and if it's a fair coin, then the number desired, or the number of heads would be 1 out of those 2. And so for a fair coin, because all the events are equally likely, then this would be the probability 1 out of 2. So that was the classical definition of probability. Another rule we talked about was the addition rule. The addition rule applies to probability with events joined by or. So probability of 2 events joined by or is probability of A plus the probability of the second event B minus the probability of both events together. Then we talked about multiplication rule. Which is the probability of A and B is probability of A times the probability of B given that A occurred. And then lastly, to find probabilities, we talked about rule of complements.
A plus the complement equals 1.
Yep, so probability of A plus the probability of its complement equals 1. Or oftentimes we use this rule to find the probability of a desired event A. So the probability of A would be 1 minus the probability of its complement. So this is when the probability of the complement is easier to find than its direct probability, and then we would just subtract them all. So of these four, basically we're going to use one of these four or some sequence of these four in order to solve this. So first of all, the first thing that sticks out is that we have a probability of events shown by or. So which rule is that?
The addition rule.
Yeah, that's the addition rule, and you have a probability of events shown by or. So that tells us that basically we're going to just add up each of the individual probabilities and then subtract out the probability of any overlap. But already, if you start exploring that, you'll see that this becomes pretty painstaking, because you're trying to find the probability of one of the samples, of the 6, being positive, and then plus the probability of 2 of the samples, 2 out of the 6 samples, so there can actually be any 2, the first 2, the second and the third and the fourth and the fifth, and so on. So just finding this probability is actually not straightforward. This is actually very painstaking, just this probability. And then the probability of the third, also painstaking, because they can be any 3 samples out of the 6. So you have to enumerate all the possibilities, and same thing for the other ones, for 5 positive and 6 positive. And then, not to mention, you have to subtract out any overlap. I'll just put this for now. So the point is that this should be the thing that immediately sticks out, because you have a probability of events shown by or. But once you start exploring it, you see that it's very painstaking. And so let's hold off on going down this thorny path and back up a little bit and see if there's another easier alternative before we dive headfirst into here. So of these other 4 rules, there's this rule of complements that say if the complement is easier to find the probability for, then all we have to do is subtract from 1 to find the probability of the event that we want. So let's see if the complement is easier to think about here. So if we have this event where the event is any of these things could happen, 1 through 6, the complement is anything that's left over. You can think of it about as the opposite, but more precisely, it's everything that's left over. That could happen if you have a sample of 6, but it's not included in this original event. So what could happen but is not included here? So 1 is positive, 1 of the samples out of 6 is positive, or 2 are positive, 3, 4, 5, 6 are positive.
None are positive.
Yeah, none of them are positive, has not been included here, so that represents the complement. That's what's left over. And that's the opposite of this situation. So 0 being positive is the complement. So if you know how to calculate this complement, all you have to do is subtract from one to find the probability of the event that you want. So in this case, it'll be one minus the probability of 0 are positive. So 0 are positive, what must that mean for each of the 6 if none of them are positive? Yeah, they're all negative, so that means the first one has to be negative, and the second one's negative, and the third's negative, and the fourth's negative, and so on, all the way up to the 6th. So, of these rules, which one deals with the ands?
Multiplication.
Multiplication rule. So now we're gonna use this multiplication rule on all 6 of them being negative. So what's the probability? So basically this is saying that you multiply each of the individual probabilities, where each of the subsequent ones are conditional probabilities. So let's step through it. So what's the probability that the first sample by itself is negative?
10% of 1 way.
Yeah, so that's given to you. Each one individually being negative, being positive is 0.1, so therefore being negative is left over from that. Yeah, which is 90%. So 10% chance of being positive, so therefore negative for each sample would be 90%. So it's left over. So the probability of just the first one being negative is 90%. So I'm gonna write this out. So the probability of just the first one being negative. And then by the multiplication rule, we're gonna multiply by the probability that the second one is negative, given that the first one is negative. Remember, this conditional probability means that you assume that what comes after the condition is true, so you assume that that already occurred, that the first sample already is negative, that's already true, it happened. Now, if that actually happened, then now you go to test the second sample, what's the probability the second sample is negative?
1.9.
It turns out to also be 0.9 because we say that those two events are independent of each other. So whether the first sample is negative doesn't influence whether the second sample is negative. So if we actually assume that the first sample is negative, and we want to find the probability that the second one's negative, then it's still 90%. So it turns out that in this case, you could have ignored the conditional probability, but you can't ignore it in general. So if you had ignored this conditional probability, it would have just been the probability that the second sample is negative by itself, which would have been also 90%. But the multiplication rule calls for you treating it as a conditional probability, and if it turns out that they're independent events, then you can ignore the condition. But you first have to treat them as conditional probabilities first. So then the next conditional probability is the probability that the third is negative, given that everything that came before it is assumed to be true. So the first is negative, and the second is negative, and the third, and the second is negative. So this means, assume the first sample was already negative, and the second sample was already negative. Now you go to test the third sample, what's the probability that it's negative? So it turns out to be, these are all independent events, they don't influence each other. So it turns out the probability that the third sample is negative is also 0.9. So each of these numbers is gonna be 0.9 that you all multiplying together. So how many 0.9s do you end up multiplying?
6.
Yeah, 6 of them. So you have 0.9 raised to the 6th power,
0.531441.
okay? And then that represents the probability that 0 of them are positive. So then you subtract from 1 to get the final probability. Okay, any questions? That's kind of, so this is kind of diving headfirst into one of the more complicated problems for these concepts. So if you're confused and not completely clear, that's okay. It just, we just started on the deep end. So what we're gonna do now is go back to the shallow end and start from there again, and then build back up to this. but because this was, asked regarding the homework, we covered it. Any questions? Alright. So of these mathematical rules that we talked about, let's start with a new example. Let's say that you take a test in this class, and let's say the test happens to be multiple choice. And let's say that there are 30 multiple choice questions. This is a multiple choice test. There's 30 questions, there's 4 choices per question. So let's say for this multiple choice test of 30 questions, let's say you Christmas tree the test, which means that you just randomly guess. So the question is, if you were to randomly guess, what's the probability that you get a perfect score and you get all 30 questions right?
10.
10 what?
10%.
Oh, 10%. Those are pretty good odds. If that was true, I would probably never study for tests and
Yeah, it
gamble
depends
that
on
10%
the
of the
person. I
time.
don't know, but I know like some people that have really good luck to where they can just
Okay, okay.
study and just.
But is it 10% of the time, like 1 out of 10 times they'll get a perfect score, even if they guess blindly?
Yeah, I mean, 4 to the 30th power is 1.15, E18.
Okay, so remember, we're trying to find this probability of a perfect score. And recall that the probability is the chances of the likelihood of something happening, and it'll go from 0% to 100%, or 0 to 1. So every probability goes from 0 to 1. Can't have a smaller number, can't have a bigger number. So let's calculate this probability together. We talked about these 4 rules so far of finding any probability, and sometimes the same probability can be found multiple ways. So in this particular case, there are 2 different ways, 2 different perspectives that you can find the same answer. So one of them is this first approach, the classical definition of probability. So this probability of a desired event or a perfect score is equal to the number of desired events over the number of total events. So let's try that. So in this case, each event is going to be each test, each scantron that you handed. So how many different scantrons are theoretically possible to hand in? How many different ways can you fill out the scantron?
3 ways? Or 4?
Well, there's 4 ways for each question, but there are 30 questions. So for example, if a test only had, let's say 3 questions, make it easy. One way that you can fill out this test is you mark all A's in the test. Another way is you mark A, B, B. Another way is you mark A, B, C. That's already 3 ways. Or A, C, C. Or we haven't even done B's yet. So A, C,
It should
B.
be 64 if you only did 3.
Right? So the question is, if there's only 3 questions, how many ways are there to fill out the scantron?
64.
Okay, good, so let's talk about it. So each of these scantrons, each of these possibilities, has 3 objects in it, the 3 that you end up filling out, and so we've been doing this horizontally. So how many options for the first question? 4. Yeah, 4. And then the second question has 4 options, third question has 4 options. So to find the total number of possibilities, by the counting rule, you multiply all these together. So 4 times 4 times 4 is 64. So if there are only 3 questions, there's 64 ways to fill out the Scantron of 3 questions. So now going back to this, if we have 30 questions, how many different Scantrons are there?
Very large number.
Yeah, very large number. So how do you get that large number?
So because there's 4 choices for each of these 3 questions, you have 4 times 4 times 4, and it would eventually be 4 to the 30th power.
Very good. So 4 multiplied by itself 30 times, which is 4 raised to the 30th power. So that represents the total number of events or the total number of possible Scantrons that can be filled out. So of those, how many represent a Scantron that's filled out perfectly with all the correct answers in all 30 questions? So only one possibility. So the probability then, using this classical definition of probability, is 1 divided by 4 to the 30th. So out of 4 to the 30th times, there's only one possibility, one time in all those times. So if you punch this in your calculator, so basically that's, so this will be 1 in 4 to the 30th power. So if you just punch in 4 to the 30th power, how big is that number?
That's what I was telling you to begin with, bro, is.
Yeah.
1.15, whole bunch of things, e to the 18th.
Yeah, so on your calculator, it says e to the 18, that means times 10 to the 18. So, yeah, that's a huge number. It's basically, 1.15 is approximately 1. So this will be 1 followed by 18 zeros. And just to give you a feel for the magnitude of that number, if we had done 1 in 1,000, 1 followed by 3 zeros, that would be 1 in 1,000. If we had done 1 followed by 6 zeros, that would be 1 in a million. And let's just multiply with 1,000 every time, add 3 zeros. So 1 followed by 9 zeros would be 1 in a billion. So we're gonna work up to 18. 1 followed by 12 zeros is a trillion. So 1 followed by 15 zeros. We're 18, so what's 15 zeros?
I don't know what follows the trillion, so right.
I need to get
Yeah, very good. So most people don't know what 3 zeros after a trillion is, because in real life we don't have numbers that big, and usually the national deficit isn't even larger than this.
Yeah.
So this would be 1 in 1 quadrillion.
Following that would be septillion.
Okay, very good. So it's so close. So 1 in followed by 18 zeros. This is all a quintillion. So QUI.
I'll hopefully pass that, sorry.
Yeah. So you notice the pattern here is every time you multiply by 1,000, it's bi, which is 2, and then tri, which is 3, quad, which is 4, quin, which is 5. So the point is that this is an astronomically large number, and only 1 part of that do you have a chance of getting a perfect score if you were to guess on this multiple choice test. Any questions? So, yeah.
So on the test, would we like to input the actual correct answer? Would we just put 1 over 4 to the 30th as the correct, like?
Yeah, the test will probably specify what it wants the answer as, and usually it's gonna be a probability of a number of between 0 and 1. So usually you would just take 1 divided by this number and put it to the number of places that's asked for. Okay, so this is one way that we can find this probability, is using this first principle that we talked about, classical definition of probability. So let's see if there's an alternative perspective here. So another way that we could do it is we could convert this situation we're trying to find the probability for. So we want a perfect score. So what does that mean in terms of each of the 30 individual questions, whether we get them right or not? So if you get a perfect score, that means
You did
that
it all right.
you got all the questions right, right? So that means that if you were to look at each question individually, that means that the first question by itself has to be correct. And so we're using and because that means on the same test, this has to be true as well, is that the second question has to be correct. And the third is correct, and so on.
Would it be easier to say and all subsequent, or do you have to do it exactly like you're doing it there?
Yeah, so logically it's the same, but we do it like this so that we can look at each event individually so that we can use the multiplication rule on each individual event. So, and so on, now that we see a pattern, all up through the 30th event, 30th question has to be correct. So now that we have a probability of events drawn by and, which of these rules applies?
Ring multiplication.
Yeah, multiplication rule. So the multiplication rule, just to be compact, just specifies with 2 events drawn by and. But obviously we don't just have 2 events drawn by and here, we have lots of events, 30 events drawn by and. But basically the principle is the same, we just go 2 at a time. So in this case, we start with the probability that the first event happened by itself. So the first question is correct. And what's that probability?
The first being correct is 0.25.
Yeah, so the probability that any one question is correct will be 1 out of 4, because there's 4 choices. So the probability the first question is correct will be 1 out of 4. And so now we're going to multiply that to the next probability in the multiplication rule, which is the probability that the second event happened given that the first event already happened. So in this case, that means the probability that we got the second question correct given the first is correct. So that means that, imagine that you guess on a multiple choice test, and imagine that you're told that you got the first question correct. So assume that that already happened, and you got the first question correct. What's the probability that the second question will be correct? Yeah. That you go on to guess the second question.
Also 1/4.
Yeah, so it turns out that it's also 1/4. And what that means is that in this situation, that condition didn't matter. So whether you get the second question correct doesn't matter, doesn't depend on whether you get the first question correct. So this condition ends up not mattering. And the probability is still 1/4 that you get the second question correct.
Unless you know a pattern.
Yeah, so then, as you start listing these out, you'll see that these are all 1/4, and then you can just multiply the 1/4 30 times. So in this case, so let's just continue so that we get a good understanding for what this multiplication rule is doing. So to fill in the next piece of the multiplication rule is the probability that the next event occurred, which is that you get the third question correct. But given that everything that came before it is assumed to be true. So given that you get the first question correct and you get the second question correct. So this means assume that you filled out the first and the second question and you were told that you got them correct. Now you go to fill out the third question. What's the probability you get the third question correct? It turns out to be also 1 out of 4, because this condition again doesn't matter. And so on. If you repeat all these, the very last probability will be the the probability that you'll get the 30th question correct, given or assuming that you got questions 1 through 29 previously correct. And it turns out, whether you get the first 29 questions correct or not, and then go to guess on the 30th question, your probability is still 1 out of 4 to get the 30th question correct. And so ultimately, it's just multiplying the same number, how many times?
30.
Yeah, 30 times. So 1/4 multiplied 30 times is by definition 1/4 raised to the 30th power. And then you could either evaluate the 1 out of 4 first to get 0.25 and then raise that number to the 30th power, or because the argument in this power is all multiplication and division, you can distribute this power across each term in the multiplication or division. So in this case, it'll be 1 to the 30th power, which is 1, and then divided by 4 to the 30th power. So notice this is exactly the same answer that we got using the other perspective. Any questions? Okay. So the first question related to this was we wanted to find the probability of getting all 30 questions correct if we guess. Now let's say that we do the question of, we want the probability that we get all 30 questions wrong. So how do you think we can approach that?
Multiplication rule's easier to do that, right? I'm trying to think of how to do it, the first one, I'm like,
Yeah, very good. So you can use any approach as long as it's reasonable.
Well, the second one, for the multiplication rule, it's really simple, because instead of being 1/4, it's 3/4, because out of 4 choices, 3 of them are wrong, that's easier to figure out. With the first one, I'm just trying to figure out, is like, probability of getting everything wrong, even if you're guessing, is still the same percentage, but how does it work up there, because there's more than one way to get everything wrong, so it's like, is that supposed to be a 3, or is that gonna be the 3 multiplied 30 times before we get to the 30th? That's why I was.
Yeah, very good. So there are multiple ways to get the same answer, but like you mentioned, sometimes one way is obviously easier than the other, in which case you should just use that way. So in this case, if you're to use the multiplication rule like before, the probability that all 30 are wrong means the first has to be wrong, and the second one's wrong, and the third has to be wrong, and so on, all the way up to the 30th question. So probability with and is a multiplication rule, so you would just multiply the probability of getting each question wrong and multiply that 30 times. So what's the probability of getting each question wrong?
0.74
Yeah, 3/4. And by the multiplication rule, just like you saw earlier, you multiply the same number 30 times. So this is a quick way to get that correct answer. So if you did it this way and you were just asked to find the answer, then you'd be done. But let's explore how to also do it the other way, in case maybe it's easier for you to think about it that way. So we're looking at the number of total events. Which we said was 4 to the 30th power before. The total number of scantrons you can hand in. And then of those, this is tricky, how many are desired? How many represent scantrons where all the questions are wrong? So there's only one scantron where all the questions are right. But how many scantrons where all 30 questions are wrong? Okay, so let's say for simplicity, you only have 3 questions. And let's say the correct answers were C, C, and C. That's a correct Scantron response. So one possibility where all 3 questions are wrong is if you filled out all 3 A's. And another one is if you fill out all 3 B's. But they don't have to be all the same, right? One can be A, one can be B, one could be D. And all of these situations represent when all 3 questions are wrong. And another one would be A, D, B, and so forth. So now that you have an idea of what these possibilities look like, the structure of them, each of these possibilities has 3 things in it. How many options for the first question being wrong? 3. How many options for the second question being wrong? 3. Third question being wrong, also 3. So now if you had 30 questions instead of just 3, you have 3 options for each of the questions being wrong. So what's the total number of possibilities to have all 30 questions wrong? 3 raised to the 30th power. So the number of desired events is 3 to the 30th power. So instead of one way to get all 30 questions right, there's 3 to the 30 ways to get all 30 questions wrong. So this is a much higher probability than before. But if you look at this and you compare it to that previous answer we got using the multiplication rule, you'll see that it's the same, because here you have a division being raised to a power. So if you have multiplication or division being raised to a power, you can distribute that power across the multiplication or division. So this becomes the same as 2 to the 30th divided by 4 to the 30th, which is the same. Any questions? Okay.
We can do a test question.
Any of these could be test questions.
All?
Yeah, these are fair game test questions.
You don't wanna go with like shorter ones every time?
So any of these would be perfectly fair game for the test. So let's do another related question. So again, you have a 30-question multiple choice test. You randomly guess on all 30 questions. Now the question is, what's the probability that you get at least 1 question right? And this is kind of similar to the example that was done on the homework with the blood tests.
Like a 50% chance.
So, at least 1 question correct is logically equivalent to what? That means you get actually how many questions right?
1 over 30.
Yeah, so either 1 question right, or 2 questions right, or 3 questions right, all the way up to possibly all 30 questions right. So 1 correct. And notice these are joined by ors because any one of these could happen. You're not requiring all of them to happen at the same time. And then all the way up to all 30. So because these are probability with or, you could use the addition rule and get the correct answer, but that's only if you use the addition rule properly. But it turns out that it's pretty hard to use the addition rule properly in this case, because you would be required to add up each of these individual probabilities, and they're not easy to find. And in truth, most of them are quite difficult to find. For example, the probability of getting 2 questions correct means that it's not just the first two, correct? It could be either the first two or the second two or the third two. Or any pairs of two, so you have to go through all those possibilities and add them all up. So each of these individual probabilities is not easy to find. So therefore, let's back up. Let's see if we can use any of these other rules, such as this rule of complements, which says that if you know the probability of the complement, you can just subtract from one to find the probability that you want. So in this case, the complement is the event that's left over. So if you're keeping track of getting one question correct all the way up to 30th, which event is left over that you're not keeping track of?
0 correct.
Yeah, 0 correct. So that represents the complement. That represents the opposite of the situation, of getting at least one correct. So the opposite of getting at least one correct is getting nothing correct. So that's the complement, and then we ask ourselves, so then we would just subtract from one from the probability of getting 0 correct. And how do we find the probability of getting 0 correct?
We just did that.
Yeah, we just did that, very good. So that was the probability of getting all 30 questions wrong, which is the same as getting 0 correct. So that was the 3/4 out of 30. That was using the multiplication rule. So this is 1 minus 3/4 raised to the 35. So in that one expression, that one operation, that will give us the right answer. And that would be exactly the same answer had we been able to use the addition rule and added up each of these individual probabilities. That would have given us exactly the same answers using the complement rule. But complement rule is a lot easier to apply in this case. Okay, any questions? Okay, let's do another example. So after you guys are done with college, a lot of you guys will end up going to grad school and have more school. And it turns out that nowadays, graduate programs or professional programs are really competitive. And so let's say the probability of getting into one of those programs so I'll say accepted into one program. Is, let's say 10%. And let's say that knowing that it's so competitive, you apply to a lot of schools. Let's say you apply to 40 schools. So all you care about is that you get in somewhere. So the question is, what's the probability that you'll get in somewhere if you apply to 40 schools? Oh, it's in? So any suggestions on how to approach this?
So your complement is gonna be the 90% of not being able to get into a school, right? So you would try to figure out what your complement is, subtract that from 1, and then that variable would be the odds of you getting into one of those 40 schools.
Okay, good. So let's summarize that. So we talked about these 4 rules of probability, and we said in particular, if the probability of the complement is easier to find, then you can just subtract from 1 and find the probability that you want. Now, getting accepted into somewhere means that either you get accepted into one school out of the 40, or 2 of the 40 schools, or 3 of the 40 schools, or maybe all 40. That's getting accepted into somewhere. So what would the complement of that situation be? What's the opposite of getting accepted somewhere? Not getting anywhere. So getting accepted into 0 schools or getting rejected by all 40 schools is the complement. So, if you know the probability of the complement, which is rejected by all 40, that sounds painful to say.
Yeah,
So rejected by all 40, if you know that probability, you can just subtract from 1, and that'll give you the probability that we want, which is getting accepted somewhere. Now, how do you find the probability of getting rejected by all 40?
The 90%, 0.9 of the 40?
Yeah, very good. Rejected by all 40 means that you have to get rejected by the first school, and the second school, and the third school. Probability with events shown by n is the multiplication rule, so you would multiply each of those probabilities together. So you would multiply the probability of getting rejected by one school, 40 times. So what's the probability of getting rejected by one school?
90%.
Yeah, 90%. Because the probability of getting accepted is 10%, so getting rejected, the only thing else that could happen by a school is 90%. So this would be 0.9, multiply 40 times, or 0.9 to the 40, subtract from 1, and go and punch that in once we get.
0.0147. How far do you want me to go?
Oh, so subtract that from 1 as well?
Subtracting from 1 as well, you get, once you subtract that from 1, you get 0.985,219,117.
Okay, good. So 0.985 as a percentage, that's 98.5%. So you notice that even though it's extremely unlikely you'll get into one school, if you apply to all 40 schools with the same odds each, it's virtually guaranteed that you'll get into somewhere. So that's somewhat surprising. Any questions?
Wait, how'd you get that 0.10 on top?
Oh, this is a given.
Okay.
Any questions, guys? So next related question, and let's say that you have jar of marbles. Let's say you have a jar of 5 marbles, and 3 of them are red, and 2 of them are blue. And let's say that you reach in and select 2 marbles, and the question is, what's the probability? Well, let's say you select 3 marbles. And you reach in and select 3 marbles, what's the probability that all 3 are red? So we select 3 marbles, and ultimately the question is the probability that all 3 are red. So in order to answer this question, there's actually something we need to specify, which is when we go into select the 3 marbles, it turns out that there are 2 different ways that we could actually select the 3 marbles. One way is if we select 1 marble at a time, note whether it's red, and then put it back. And then select the next marble, put it back, select the next marble. That's called selecting with replacement. And so we're going to do this 2 ways. One is we select with replacement. That means that the marble you select, you replace it after you selected it. But usually when you select a number of things, like 3 marbles, you don't put them back each time, you actually grab them all in one hand. And technically that's without replacement, because each of those are not getting put back before the next one is selected. So usually we select without replacement, or all at once. But let's do both cases. And it turns out, regardless of which of these two cases, whether it's with replacement or without replacement, the approach will be the same, in that if you're selecting 3 marbles and you want all 3 to be red, that means the first marble has to be red, and the second is red, and the third is red, right? So, this is the probability, the first is red, and the second is red, and the third is red. Right. So we have a probability with events drawn by n, which rule is that?
Multiplication rule?
Yeah, multiplication rule, which says that it's a probability of the first event times a conditional probability of the next event, given that everything that happened before it is assumed to be true. So, in this case, this will be the probability of just the first event by itself, where the first is red, times the probability of the next event, which will be conditional, which is the probability that the second marble is red, given that the first is red. And then times the probability of the next event, which is the third marble is red, given that everything that came before it is assumed to be true. So the probability that the third is red, given that the first and second were red. So regardless, if we select all 3 marbles with replacement or without replacement, this approach will be exactly the same. It's still the multiplication rule of all 3 marbles being red. So now, let's look at each situation at a time, with replacement and without, and see how they differ using this multiplication rule. So let's fill in the numbers. So if we were to do with replacement, we put a marble back each time. What's the probability that the first marble by itself is right?
3 and 5?
Yeah, 3 out of 5. And then we go to put that marble back, whether it's red or not. And now we look at the next probability, assuming that that first marble was red, but then you put it back. Now what's the probability that the second marble you go to select is red?
3 out of 5.
Still 3 out of 5, because whether the second marble is red doesn't depend on whether the first marble is red, because whether it's red or not, you put it back anyway. So it's still 3 out of 5 that the second marble is red. What about the next case? Assuming that the first and second marble were both red, but then you put them both back, what's the probability the third marble that you go to select is red?
3 out of 5.
Still 3 out of 5. So in this situation, which happens to be with replacement, the probability that all 3 marbles are red will end up being 3/5 raised to the third power. Any questions?
When we answer a question like this on the exam, do they want it in a fraction raised to the power, or do they want a decimal point to however many places?
It should specify.
Okay.
Okay, so the next question is, let's say now we select the 3 marbles without replacement. So essentially, we're selecting all 3 at once, not putting each back as we select it. So now we use the same multiplication rule and answer this question of what's the probability that all 3 are red. So the first probability is the probability that just the first marble is red. So what's that probability?
3 out of 5.
Yeah, still 3 out of 5. But now, this next probability, which is conditional, is we assume that the first marble that we select is red, and we didn't put it back. So now there's 1 less red marble and 1 less marble total. Now, when we go to select the second marble, what's the probability that that second marble is red?
2 out of 4.
2 out of 4, very good. So, because there's 1 less marble total and 1 less red marble, there's 2 red marbles out of 4 marbles total. And you see in this example that this conditional probability really makes a difference. And so now you go to the next conditional probability, which is assume that the first and second marbles were red and you didn't put them back. Now you go to select the third marble. What's the probability the third marble's red?
1/3.
Yeah, very good. So one red marble out of 3 total. So this would be the correct answer if you multiply everything together. If we simplified, we could divide the 3's out and we'll get 2 out of
20.
2 out of 20, which is 1 out of 10. Yep. But we don't have to simplify. I'm just going to leave it there so you can see the numbers. Okay, any questions so far?
I thought it would have been, 3 factorial over 5, factorial.
Okay, this is an interesting comment. So the way that we did this was the multiplication rule. But another way that you could have done it is you could have used the classical definition of probability on this example with or without replacement. So since that was mentioned, let's explore that perspective.
You did give me the right answer though, that's why I was.
Yeah, so let's talk about that. Okay, so let's do this case of selecting all 3 marbles at once without replacement and find the probability that all 3 of them are red. And we're going to use this perspective of the classical definition of probability. So number of desired events divided by the number of total events. So in this case, one event is the 3 marbles that you're grabbing all at the same time. So the question is, how many different ways are there to select 3 marbles from 5? Or 3 numbers from 5? And the question is, do you care about the order of the numbers within each group of 3 that you select, or do you only care about the identity of the numbers, or the identity of the marbles?
You only care about the identity.
You only care about which 3 marbles you grab, you don't care about their order. So therefore, that'll be a combination. So the total number of events, or the total number of ways that you can select 3 marbles from 5, where the order of the 3 marbles doesn't matter, will end up being 5, choose 3. So of those number of total events where you're choosing 3 marbles from 5, how many represent a desired event where you have all 3 red marbles? Yeah, there's only one way to get 3 red marbles from these 3 red marbles. Another way to think about it is you're choosing 3 red marbles that you want from 3 red marbles total. So 3 choose 3 ends up being 1. So the number of desired events will be 1 divided by this number. And 5 choose 3 should be 10. So this will be the same answer that you get down here, and if you simplify this, you'll get 1/10 as well. So this is another way that you could have gotten the same answer. Any questions? Okay, so related to this, let's do a similar example. Let's say now, instead of having a jar with 3 red marbles and 2 blue marbles, you have a really big jar with 3 million red marbles and 2 million blue marbles. And you have this giant jar, this giant vat of marbles. And we ask the same question. We go in to select 3 marbles, and we want to know the probability that all 3 are red. And we're going to do, again, both scenarios, where one is with replacement and one is without replacement. So the scenario with replacement. So if we choose to approach this using the multiplication rule, the same multiplication rule will apply in both cases. We want all 3 marbles to be red, so using the multiplication rule, it's the multiplication of this first term, which is probably the first marble by itself is red. So what would that be? You have 3 million red marbles, 2 million blue. What's the probability that you select one marble and it's red?
Is it still 3 out of 5?
Yeah, it's 3 million divided by the 5 million total, so still 3 out of 5. It still simplifies to 3 out of 5. And because it's with replacement, you put it back before you go and select the second marble. And so in our multiplication rule, this next term is assume that the first marble is red, but because it's with replacement, you put it back. And now you select the second marble, and what's the probability the second marble is red?
3 out of 5.
Also 3 out of 5. And same thing for that last probability of assuming that the first 2 marbles are red. What's the probability that the third marble you go to select is red, and it's still 3 out of 5? Because it doesn't matter what the first 2 marbles were. They're independent of the third marble being red, because you put them back. So this is also 3 out of 5. So you notice that with replacement, no matter how many marbles there are, 5 or 5 million, you're still gonna get the same probability. So this is 3/5 raised to the third power. Now let's go to do the second case of without replacement. So you're grabbing all 3 marbles at once. I would do the same thing, use the multiplication rule. So the first term here is probably the first marble by itself is red. 3/5. So 3 million out of 5 million. But now, this is where the difference comes in, is if you look at the second probability, which is conditional, this is given that the first marble is red, but this time it's without replacement, so you don't put it back. So now there's gonna be 1 less red marble and 1 less marble total. And now you go to select the second marble, and what's the probability that the second marble is red?
A really big fraction.
Okay, so what would it be?
2,999,999
Okay, good.
divided by 4,999,999.
Good, so you're subtracting 1 each time from really big numbers. So 2,999,999 divided by 4,999,999. This should feel a little bit ridiculous, but we'll talk about how to address that. And then times, so the last term in our multiplication rule, which is given that the first 2 marbles are red, and you didn't put them back, so now there's 2 fewer red marbles and 2 fewer marbles total. Now you go to select the third marble, what's the probability that third marble's red? So subtract 1.
Yeah, 2 5 9s and an 8 divided by 4 5 9s and an 8.
Okay, so subtract 1 from the previous numerator and denominator. Okay, so the reason we had to do this is because these are not independent events. So, because in this case, we had without replacement, then each of these conditional probabilities, whether a second marble is red, is dependent on whether that first marble was red, because there will be 1 less red marble. So you can't ignore this conditional probability. So because of that, we ended up having to subtract 1 from both the top and the bottom of these gigantic numbers. But that should feel a little bit ridiculous, because this final fraction of 2,999,999 divided by 4,999,999 is so close to 3 out of 5, we might as well call it 3 out of 5. So this is virtually 3 out of 5. So we're gonna just approximate this as 3 out of 5. And same thing over here, this is so close to 3 out of 5 that we might as well call this 3 out of 5. But if we do that, then we're actually assuming that these are independent events. We're assuming that these conditional probabilities ended up not mattering, and whether a second marble was red was independent or didn't depend on whether the first marble was red. So if these numbers representing conditional probabilities are the same as a number that represents a non-conditional probability, then we say that the events are independent of each other. And so, in this case, we can actually assume or approximate that the events are actually independent. And we'll get an answer that is virtually the same as before. And so we have a rule for this. This is called the 5% rule. So the 5% rule the 5% rule says that if the sample size is small enough, and the way we quantify small enough is if it's less than or equal to 5% of the population size, then we can assume that each of the individual draws of the sample are independent from each other. So let's apply this 5% rule on this example. So in this example, what's the sample size and what's the population size? So the sample is how many you actually select out of the total, which is the population size.
So you're selecting 3.
Yeah, you're selecting 3, so the sample size is 3. And then what's the population size?
Well, the first one is
Yeah.
5, and the second one is 5 million.
Well, you're only selecting 3 marbles at a time, so that's your sample. So your sample would be 3. And then your population size would be everything, which is 5 million.
I thought we were comparing both, my apologies.
Oh, yeah. So 5 million? Yeah, so the question is the sample size of 3 less than 5% of 5 million?
Yes.
Yeah, it's a lot less, right? So because of that, we're allowed to treat each of these samples as being independent from each other, which mathematically means we can use the same probabilities over and over. So let's look at the previous case that we did, where we only had a jar of 5 marbles and we selected 3. And down here, we ended up saying that the probability that all 3 are red has to be the product of these very different 3 fractions. So in this case, intuitively, would you have been able to say that 2 out of 4 is so close to 3 out of 5, might as well call it 3 out of 5? Or 1/3 is so close to 3 out of 5, might as well call it 3 out of 5? No, because they're not close. So you would not have been able to just call each of these numbers 3 out of 5 and get an accurate answer. So one way to quantify that is this 5% rule, which says that if the sample size is less than 5% of the population size, then you can treat them as all the same number. But in this case, what's the sample size, what's the population size? Yeah, the sample size is still 3, but what's the population size?
It's 5.
Yeah, it was a jar of 5 marbles.
Which was 60%.
Yeah, so 3 is 60% of 5, not less than 5%. So therefore, you can't use the 5% rule here, and you can't treat each of the draws of the samples being independent, and you can't use the same number
representing a probability of success each time. So you can't use the 5% rule here. Okay, any questions?
That makes much more sense to me, because I actually did all the big fractions and put it together, and I'm like, between the two, it's not the same at all, when you go for the second one without replacement, because you end up with literally like 21%.
Yeah.
Instead of 1/10.
Yeah.
I'm like, that didn't make sense, so where are we going with this?
Yeah. Okay, good. So with these examples, we covered the multiplication rule. And then we talked about the effect of these conditional probabilities within the multiplication rule. And we said that even though you always have to use the conditional probabilities in general, sometimes the conditional probabilities work out where the conditions don't matter. And having the condition is the same as not having the condition. And when that's the case, we say the two events in the conditional probability are independent of each other, where you can ignore the condition. And so this 5% rule gives us a quantification of when you can ignore that condition, i.e. when the events are independent of each other. And that happens if the sample size is small enough, if it's less than 5% of the population size. Then for each of these conditional probabilities, you can just use the same probability that was a non-conditional probability, and just use that same number over and over if the 5% rule applies. Okay, any questions? All right, so hopefully you feel a little bit more confident about these probability rules we talked about, having applied them. Any questions?
What is going to be allowed on the test before we go home and try to open up on what I'm reading this? Because I remember you saying there was something like a list of formulas, like sigma or something like that, that we'll be able to use, or not, depending on how this test is set up.
Yeah, so you can use your book, it's a totally open book. And if you don't have a physical copy of the textbook, you can use the ebook that's provided with your access code. And you can open up another browser tab with the ebook right next to your test. That's fine. So the test is open book. It's not open notes. And philosophically, I don't have a problem with open notes. The problem is that everybody has the same textbook, so I can standardize what's available to everybody. Versus notes, people sometimes abuse that. They just print out everything that's on the internet. and so it's hard to standardize that. So it's not open notes, but it is open book. You can also use any handheld scientific calculator, including a graphing calculator. You can't use a cell phone, you can't use an iPad or a tablet, anything with Wi-Fi capability. You can use Excel, but a calculator is recommended. You can't use StatCrunch or any other software. You have 3 hours for the test. For 25 questions. So this test bank, for every test that is made up, also gives the time that it takes the average student to complete the test. And the average student completes this in a little bit over an hour, and I'm giving you 3 hours. So just so you know, don't feel rushed. Take time to check your answers, and don't feel rushed. Any questions?
And I'm just asking because there are different ways that this can set up, is there a pause option, once we start taking the test, or once it starts, you have 3 hours to complete the test period?
Yeah, so once it starts, you have the 3 hours.
Are we allowed to just pen and scratch paper to write stuff?
Yeah, you're allowed scratch paper, so just blank paper.
Maybe take test here.
No.
You can't write it on the board. Like,
Yeah, so you can take, the test behind any computer, but, don't, expect me to be there.
Will we be required to
Yeah.
submit our notes from the, or our scratch paper from the test?
Only if there's an issue later, but you're not, automatically, so just go ahead and hang on to your scratch paper, until a couple days after next.
yeah. If I get that 100.
All right, good luck, guys, and feel free to email me for help anytime. All right, looking forward to it.
Not during the
That's it.
Yeah, it's not during.
I didn't catch multiple choice, obviously, it was like.
No, it's just, yeah, it was similar to your homework questions where you enter in the correct number.
He probably knows.
Is there tutoring on Fridays?